Welcome to today's Explainer. Have you ever wondered why the absolute smartest AI models out there are just insanely expensive to run? I mean, for years, the industry's go-to solution for better AI was basically just brute force, throwing massive, incredibly expensive piles of hardware at the problem. But today, we're tearing down a truly fascinating piece of engineering that completely flips that script, the Kimi K3 architecture. We're going to see exactly how K3 solves some massive scaling constraints, not with more servers, but with pure, elegant architecture.
So that brings us to the literal billion-dollar question that is keeping top-tier engineers awake at night. How do we actually scale AI without melting our servers? Because right now, when you try to force-feed a standard model more data, it hits a physical wall. Memory requirements absolutely explode, internal communications jam up like rush hour traffic, and efficiency just drops right off a cliff. We desperately need a new way forward.
Okay, let's dive right into this specification sheet on the screen because the numbers here are wild. Notice the massive delta between the baseline and K3. K3 literally doubled its parameters from 7 billion to 14 billion, and it more than doubled its training data, jumping from 1.2 trillion to 2.5 trillion tokens. But here is the jaw-dropping part. Look closely at that hidden dimension row. It didn't go up. It actually shrank, plummeting from 4096 down to just 896. How is that even possible? Well, they did it by completely redesigning the underlying plumbing into a stable, latent mixture of experts. They didn't just make the pipes wider, they completely reinvented how the pipes work.
Here is our roadmap for this explainer. We'll start by defining the AI scaling bottleneck, look at the Kimi K3 blueprint, and then unpack its three main pillars: solving memory, mastering depth, and perfecting routing. Finally, we'll see how it all adds up to doing way more with less.
All right, Section 1, the AI scaling bottleneck.
Look, in traditional setups, trying to scale up turns into an absolute nightmare. First off, memory gets exhausted incredibly fast. The KV cache just grows exponentially until it essentially crashes under its own weight. Second, as these neural networks get deeper, the original signal starts fading. It's kind of like a giant game of telephone across hundreds of layers. And third, you get these catastrophic routing traffic jams where one part of the network gets massively overloaded while the rest of it is just sitting there completely idle.
Moving into Section 2, the Kimi K3 blueprint. And this diagram right here brilliantly illustrates exactly how K3 tackles those exact bottlenecks. Notice the K3 core at the top, delegating down into three distinct independent pathways. On the left, it solves the memory issue through a compression funnel called KDA. In the center, it solves the depth issue using block attention residuals to loop historical context. And over on the right, it fixes routing with LatentMoE and quantile balancing. It's a comprehensive, three-prong attack.
Let's break those down, starting with Section 3, solving memory with KDA.
Check out this visual of the compression funnel. This is Kimi Delta Attention, or KDA. Instead of hoarding massive, heavy blocks of memory like older models, KDA uses two pretty brutal filters. Filter 1, the Delta rule, acts like an incinerator. It literally burns up obsolete memories so they don't clog the system. Then, Filter 2, the Forget gate, controls the exact lifespan of whatever is left. The result? All that heavy raw data at the top gets compressed down into that single, hyper-dense state you see at the bottom, marked as S.
Now, if you're wondering what to call this, it's defined as linear attention. Think of it like reading a super concise summary instead of having to reread a massive 1,000-page book every single time you need to recall one specific fact. By merging all that past context into that single compressed state S, the system never has to go back and fetch historical tokens one by one. It is a massive, massive efficiency leap.
But as you might guess, heavy compression can sometimes sacrifice granular detail. So K3 introduces this really clever hybrid engine. Notice the repeating sequence on the slide here. You've got three highly precise MLA layers, followed immediately by one compressed KDA layer. By weaving them together in this strict 3-to-1 ratio, the model hits this perfect sweet spot. You get the exactness of standard attention, but with a drastically lower overall memory footprint.
Next up, Section 4, mastering depth with residuals.
Now, what's really interesting about this slide is the sheer visual contrast. Look at the standard architecture up top. It is a mess of overlapping red lines, right? Every block is constantly querying past blocks, which creates this massive redundant I/O nightmare. But look below it at K3. It uses a clean, zero redundant blue arrow. Past blocks process completely independently, creating a single forward state that feeds the internal computation. It's so much cleaner.
And they pull off this clean processing using what's called two-phase inference. As you can see mapped out here, phase 1 handles the past. It essentially throws a single batched query at completed blocks to gather statistics. Then phase 2 handles the present, focusing its computation strictly on the active block. By totally decoupling the past from the present like this, they achieve a 1.25x jump in speed, and they do it without losing a drop of signal integrity.
All right, Section 5, Perfecting Routing with Cube B.
So in the past, preventing these internal routing experts from burning out meant engineers had to rely on exhausting manual trial and error, literally guessing and checking hyperparameters just to stop the servers from crashing. Well, K3 throws that manual labor completely out the window. It replaces it with a hyperparameter-free statistical approach called quantile-balancing. Let's look at how this builds out visually on this distribution curve. See that massive red spike on the left? Without quantile balancing, that is a single node overloading, which crushes the system. But quantile balancing steps in like a dynamic traffic cop. It analyzes the data routing in real time and automatically applies a negative bias to any overactive experts. The result is that smooth green curve you see, which mathematically guarantees no single expert ever gets overwhelmed.
Which brings us to our final part, Section 6, Doing More with Less.
So, bringing this all together, the crucial takeaway is mapped out on this diagnostic table right here. The old rules dictated that managing deep context meant you had to exhaust your memory. K3 beat that with the KDA 3.1 hybrid. The old rules said deep layers meant losing your signal. K3 fixed it with block residuals. And standard routing meant guaranteed heavy bottlenecks. K3 bypassed that entirely with LatentMoE and quantile balancing. The table really proves the point. K3 successfully trades brute force hardware scaling for pure architectural genius.
Which leaves us with a pretty massive question to think about. If we have officially reached the point where architectural elegance can completely outperform brute force scaling, what exactly does the next generation of frontier models look like? As hardware constraints get tighter and tighter globally, it really seems like the true edge in AI won't belong to whoever has the most servers, but whoever has the smartest blueprints. Thank you so much for joining me for this explainer. Keep questioning the architecture, and I'll see you all next time.